Today I will present to you our collaborative work between the University of Sussex and University of Bristol. It is TastyFloats, a contactless food delivery system. But first, let me show you a short movie clip. Okay? Okay, I've seen these movies multiple times, also during the preparation, but still quite amazing, isn't it? It is super to have this kind of skill to like impress your girlfriend or partner during dinner, I guess. But how can we do this? Of course, without being trained as a Jedi, like Anakin here. We are SIGCHI researchers and engineers. What can be our forces? So that's why in this work I will present to you TastyFloats. Okay. So the first question you will ask is what is TastyFloats anyway? So TastyFloats is a concept consisted of three parts. It has pickup, transportation, and then it has delivery part. This design is based on the fact that food has three stages of the preparation, where the chefs prepare the dishes, and then the transportation stage, where the waiter carries the food from the kitchen to the customer, and then delivery stage, where the customer enjoys the food. Okay. So TastyFloats use the principle of acoustic levitation to levitate the food. So in simple terms, acoustic levitation is a process of holding and moving an object in midair. So as you can see in the picture on the right here, a simple system setup of acoustic levitation typically includes a emitter of high frequency waves, which is the one on the top there, and then a reflector to reflect the waves back. To create a standing wave with nodes and antinode interleaved with each other. So if the acoustic pressure at these nodes are strong enough, it can defy the force of gravity and allow an object to place in the middle to float in midair. So you can see a demonstration on the right here. However, this is not the only way to levitate food. The levitation of food has been tried before. For example, you are seeing here is static levitation of food using magnetic approach. So on the left here is the levitation of a sea urchin. On the right here is the device from levitating eggs, that is levitating a sushi dish. So however, as you can see here, the levitation is done by levitating the plate, not levitating the food itself in the examples. But you may want to ask, what's the problem with this, right? So the problem here is because the food is placed on a levitating dish, it must be eaten using cutlery. So in other words, they only consider the final presentation of the food, and not the whole delivery chain from the kitchen to the customer, which has three stages, as I explained before: the food preparation, transportation, and delivery. So in the context of acoustic levitation, it has been used to levitate small living objects or small living animals in airs, such as the example you're seeing here is the levitation of ant on the left here, and with ladybugs and young living fish. Okay, they're all still living at that stage. Okay. Here is an example of a levitron that levitates a cocktail of gin and tonic. And then the example of levitation of crystallized Heinz ketchup. Okay? So the last two examples here are cool because they show that it is possible to levitate food, right? However, it is still only static levitation. Again, it does not show the three stages of food preparation. So we are still not Anakin Skywalker yet. how can we be a Jedi now to Padme. Okay, so this is early implementation of TastyFloat. I know it does not look pretty, but it's our first prototype. So it incorporates 3 stages of the food. As you can see, the red transportation unit there, where the food are injected into the unit, it is transported along and released on the other side of the unit. Okay. So, however, to do this kind of implementation, we face 2 kind of challenge. The first one is technical, and the second one is perceptual challenge. So let's first focus on the technical one first with some examples. Okay, so to solve this technical problem, TastyFloats should adjust its control parameter adaptively to what kind of food it is placed in there, and also take into account the surrounding environment as well. So let's first look at some mathematics of the acoustic force inside the unit. Okay, so in equation 1 here, it shows acoustic force to levitate a food morsel. So this force this force depends on the radius of the particle that is being put in there, being levitated, and also the compressibility of the levitated morsel in the air, and the pressure and the velocity in air due to the emitted acoustic force, acoustic wave. As well as the ratio of the density of the food and the air. Okay? So with the assumption that there is a one-dimensional size standing wave, in particular here, in the z direction, and then the density of the food and the liquid morsel is much greater than air, so we have the minimum acoustic force depend on the density of the levitated food morsels and air, and also the wave number and the speed of sound in air here. Okay, so in the case of in the case of liquid droplet, which is example of water, milk, ethanol, and wine here. So we found out that okay, where's my mouse? Sorry. Okay, this way, yeah, okay. So we found out that same acoustic levitation, they have the same acoustic levitation contrast factors in air. So it means that what happened inside a droplet does not change acoustic pressure to levitate it. And also we show that once levitated, they will have different equilibrium state. So for example, milk droplets, are predicted to be more spherical than the equivalent droplets of water or ethanol. And also, we show that larger pressure are needed to levitate larger droplets. And finally, we show that when we apply a acoustic pressure to the droplet, will increase its temperature and also evaporation. In the case of, for example, here, ethanol is the most sensitive one, as it requires less energy and to vaporize, and it boils earlier. So when we levitate a food morsel, the voltage that we apply to the unit in order to levitate the morsel, it depends on the property of the morsel, given that we are keeping the environment constant. Such as the volume of the food morsel is the most important factor in here. So this kind of consideration should be taken into account by the control software. Let's move on to the release of the food morsel once it's inside transported, and at the end of the transportation in it can be released. So here we show the velocity of the morsel once it's flown out of the unit onto the air, onto the customer plate or the customer's tongue, for example. So we have the the coordinates of x and y here, the equation of x and y, and based on this, we calculate the falling distance and terminal velocity, which will depend on the drag coefficient, the volume radius of the food morsel, its density, and also the acceleration of gravity. Okay. So for example, when we release a 5 microliter droplet of y, it is expected to reach the falling distance of 20 to 30 centimeters, as well as the terminal velocity is about 7 to 8 meter per second. Okay. So in our design parameters of a complete TastyFloat system, the customer will first choose, okay, I want this item on the menu, ice cream, and this choice will be fed into a system where the software controller in the middle here will look up the food density and take into account the environment parameters such as air viscosity and density, and then it sends the command to the TastyFloat system with the path and the speed required to deliver a tasty experience, along with the pressure and voltage needed for the system to levitate the food, and also how many bits of food is required to chop up the food and send it along the way. Okay, so let's see some example of TastyFloat in action. Okay. So once the first challenge is solved, the next challenge come up. The question now is what is the effect of acoustic levitation on our user, on our taste perception, right? So if we taste the levitated food, how does it taste like? Can we still perceive the taste as it was put in there, and when we like the taste in there? So to answer this question, we designed a user study. So in this user study, we use a variable of 3 basic tastes, which is sweet, bitter, and umami. And then 3 volume size of the droplet we put in there, which is 5, 10, and then 20 microliter. And then we compare between the 2 delivery mechanisms. One is using pipette on the left there, and the other using acoustic levitation, where the participant will take the levitated bit. And then we ask the user if they perceive the taste in there, and then how intense the taste was, and whether they feel pleasant with it or not. Okay, so our preliminary findings show, in terms of recognition rates, participants recognize the most with sweet taste, which is about 86%, and then followed up by umami taste, 70%, and then the bitter taste is the least recognized taste here with about 46%. And interestingly, we found that levitated tastes are significantly more intense compared to the pipette condition. And also about the pleasantness, surprisingly, we found that levitated bitter is more pleasant, given the fact that it was unpleasant outside here. We normally don't like bitter taste, at least for me. And also the pleasantness of sweet was lower than the baseline score. And about the satisfaction, that we found that sweet is slightly satisfying, and bitter and umami are slightly unsatisfying. Yeah. So in summary, we present here the TastyFloat concept that can adaptively levitate different types of food, solid and liquid, as well as single or multiple food morsels. we initially implemented the system, the TastyFloats system, and then investigated the effect of acoustic levitation of 3 basic tests on our taste perception. But the next question you may want to ask is what's the application or future work of this one? In our future work, TastyFloats can be applied to deliver molecular gastronomy inspired desserts, for example, to stimulate our taste palette with different types of sweetness. Or it can also be used in VR to deliver a multi-sensory experience, such as a burger. You saw an example of a burger before. But it can also be combined with smell, another chemical sense, to deliver a rich flavor experience. Another example is it can be implemented at the airport while we are waiting for our next flight. We can enjoy different type of food, or maybe a coffee, espresso at Starbucks, while we are waiting for our flight. Okay, thank you.
Work. I was wondering if your user study was blindfolded, like did the participants know whether the food that they were tasting was levitated or not?
So they will see the food levitated or not, because we divide into 2 conditions, right? Okay. So we did not cover their eyes, but a participant did not know what taste it was, because we asked them to turn around when we put the taste in there, so the participant have no idea whether they will have a sweet or bitter or umami taste.
Okay, and so I didn't understand how it worked. So did they taste bitter, like in a levitated condition, and then the next condition?
We divide into 2 different conditions in a counterbalance order between participants. Okay. So each participant will either go to complete the levitation condition first, and once they complete it, they can move the pipette condition, and the next participant can do the pipette first and then do the levitation.
Yeah, I was wondering if they didn't know like the source of the food, and then how would they perceive or describe the taste?
Well, we asked them about the first criteria, right? So whether they recognize the taste we put in there. So we keep track of whether, okay, this trial I put sweet taste in there, did the participant recognize it or not, and how intense they feel on the scale, and then how pleasant they feel on the scale, and we compare between 2 conditions of the levitation and pipette. Yeah. So besides that one, we also ask them for opinion or open comment at the end. Yeah.
Okay, thanks.
Yeah, thank you.
So this follows on from there. I was wondering, and it's just a question I'm asking myself now. I guess with the pipette, somebody else gave it to them?
I gave it to them, yes.
Whether that made a difference, because having done the demo, you have to do it yourself and put out your tongue.
Yeah.
So in terms of action perception loop, you are in control of when, or roughly in control of when you're getting it, whereas with the pipette, it's given to you and it's kind of a surprise whether that might actually have an effect on the acuity of distinguishing the taste. I don't know, but it would be something that maybe it's worthwhile looking into.
Yes, I think it's definitely a good point. Yeah. Any other?
Something that I was wondering, like the levitation depends on the density, and it's also something that sort of connects to food. Like food is meant to be warm.
Yeah.
While it is being delivered, and it's also it tends to spin.
Yes.
And being such a small size, it's probably going to cool down. So, am I gonna get my food cold?
Oh. No, the fact is not. You will get your food hot. So the fact one possible explanation that why the taste in the levitation here feel more intense is because we show that the food is being levitated when get heating up slowly due to the induced energy to levitate it. you will get it hotter than normal. This thing like you are eating, you're cooking in microwave, right? And then you're eating it in the same time. Yeah.
Like my other question was sort of going to connect on the first one, because also like with temperature, density could change, and then maybe like the pressure wouldn't be enough. But I guess you just sort of reply if you're heating while it gets cold. It's okay. Cool. Thanks a lot.
Yeah. Thank you.